All right, so yesterday we skipped number 3, looking at a multiple angle, so I want to do that one today. So we want to solve the tangent of 3x is equal to 1, and we want to solve that on the interval between 0 and 2 pi. So we're not looking for every single solution. We're just looking for the ones within one rotation on the circle. And so we cannot divide this by 3 in order to get that x by itself. Because remember, we are taking the tangent of 3x. That's why we had the double angle formulas and things like that, because you can't simply divide it by 2. We have to undo the tangent first before we do that. So what we're going to do instead is we will take this out and replace it with something else. Let's just call it theta. So we want to know, where does the tangent of theta equal 1? Now, don't forget, I mentioned this yesterday. The period for tangent is just pi, not 2 pi. So we only need to look from 0 to pi, because then it's going to repeat after that. So between 0 and pi, you're looking on your unit circle, so we're looking at quadrants 1 and 2. The only place where the tangent of theta is equal to 1 is at pi fourths. So that means that theta would equal pi fourths plus pi n. Now, the reason we're only adding pi n this time is, again, because the period for tangent is only pi. So we're adding multiples of just pi this time. That's the only place that you get positive 1 in between 0 and pi. Then it would start to repeat again. But so here's the difference. We weren't really trying to solve for theta. Remember that theta was originally 3x. So what we're doing now, and I'm going to move this over here to leave myself some space, and you'll see why here in a second, is we know that 3x is equal to pi fourths plus pi n. And so now we need to go ahead and solve for x. So what we'll do is we'll divide everything by 3. We'll divide by 3 here, divide by 3 here. Now don't forget that when I do pi fourths divided by 3, when you keep change flip, that means times 1/3. So we're going to get pi twelfths. And so what we have is x is equal to pi twelfths plus pi thirds n. Okay, so here's where this gets a little bit tricky. We didn't really see any like this yesterday, but because we want to know all the values between 0 and 2 pi where this would work, we need to plug in multiples of n until we get a value that exceeds 2 pi, and then I know that I am finished. So for example, not really for example, this is what we're going to do. We will start with when n is equal to 0. If n is equal to 0, that's just going to give me pi twelfths. So that's my first answer. If n is equal to 1, then I have pi twelfths plus pi thirds times 1, which is just pi thirds. I need a common denominator here, so that would give me 4 pi over 12 multiplied by 4 over 4. And so when I add those together, I get 5 pi over 12. That is still within my 0 to 2 pi, so I need to keep going. So we'll try when n is equal to 2. I have pi twelfths plus pi thirds times 2 would be 2 pi thirds. Again, multiply by 4 over 4, that's going to give me 8 pi over 12. And so this gives me 9 pi over 12. Now, since we're adding, that's going to reduce, by the way, to 3 pi over 4. But since we're adding the same multiple over and over again, you can see that we're starting to get a little bit of a pattern forming here. From pi twelfths to 5 pi twelfths, we added 4 pi twelfths, because we're adding a pi third, so that should make sense. From here to here, we added plus 4 pi twelfths. So we can keep doing that over and over again until I get a value that's bigger than 2 pi. Now think about what 2 pi would be in twelfths. If I have 2 pi over 1 and I want to change that to twelfths, I'd have 24 pi. Uh-oh. Got it. I'd have 24 pi over 12. So we have to be lower than that for it to be an answer that we can count. So if I keep going, 9 pi twelfths plus another 4 would be 13 pi twelfths, still good. Then I would get 17 pi twelfths, still good. 21 pi twelfths. That one is going to actually reduce to be, let's see, we can divide them both by 3, so that gives me 7 pi fourths. If I add another 4, I'm going to get 25 pi twelfths. That's too big. So here are all of the possible solutions between 0 and 2 pi that would make the equation tangent of 3x equals 1 true. So for each one of those, we did when n equals 0, n equals 1, n equals 2. We noticed a pattern after that, but this would be when n is 3, when n is 4, when n is 5. When n is 6, we end up with something that is bigger than 2 pi, so we're done. So 6 possible solutions there. Now, these are a little bit tricky, so I want to go ahead and do one more, even though it's not in your notes. If you feel like you've got it, go ahead and skip ahead. But let's go ahead and look at another one real quickly here. All right, so here's one. The sine of x over 3 is equal to 1/2. So again, what we're going to do here is imagine what the solutions would be to if I had sine of theta equals 1/2. So again, look at your unit circle, and from 0 to 2 pi, tangent is the only one where we just look at half the circle. Sine, we're back to the whole circle again. So from 0 to 2 pi, the sine is 1/2 at pi sixths plus 2 pi n. And that is also true for 5 pi sixths. 5 pi sixths plus 2 pi n. This one is actually, sorry. So this one is actually going to be a little bit nicer because remember theta was really x over 3. So that's what we're looking at. X over 3 is equal to pi 6 plus 2 pi n, or x over 3 is equal to 5 pi 6 plus 2 pi n. To get rid of dividing by 3, we're going to multiply everything by 3, which is probably easier than trying to divide. We're going to do that to every single term. So for this one, we get x is equal to 3 over 6 reduces to 1 over 2, so we get pi halves plus 6 pi n, and we get x is equal to 5 pi halves plus 6 pi n. And now here's the thing, if I add 6 pi to either of those values, I'm automatically going to exceed 2 pi. And the domain that they wanted was from 0 to 2 pi. If it hadn't, then I would start again when n equals 1. And I would have to work both of these equations until I got every single one that did not exceed 2 pi. So I would probably just start with the first equation, keep going until I got bigger than 2 pi, then go to the second equation to see if I get any different ones. Sometimes you're going to find that the second equation just cycles through the same solutions. If you notice that's happening, then you can kind of abandon ship there. But if it's giving you different solutions, then you would need to keep going. But again, if I went to do pi halves plus 6 pi, that would be 12 pi over 2 with a common denominator. I get 13 pi over 2, which is bigger than 2 pi. So that's how I know that I'm done. So my only two solutions would be pi halves and 5 pi halves. That's the only time that that's going to happen between 0 and 2 pi. Okay. We are going to look at one more type today, which is trig functions that are in quadratic form. And so you're going to have to think back to everything you know about factoring. So remember that a quadratic is going to be in this form here. And what we're going to use is that same idea of U substitution that we've used multiple times throughout the year. So to solve this, we're going to have to factor it if we can. That's always going to be the easiest. If we can't factor, then we can use something like the quadratic formula or maybe solving by square roots. But we're going to have to do something. Now, if you don't remember the quadratic formula, you might want to jot this down. Opposite of b plus or minus the square root of b squared minus 4ac. And then all of that is over 2 times a. You may want to have that for reference later. So here's what I would do. We are going to let u represent the cosine of x. That means if I take that out, I've got 2 times, instead of cosine squared of x, I would have u squared, plus u, because that's our cosine of x, minus 1 equals 0. And I'm going to solve that equation without worrying about my cosines yet. So we can see if this is factorable by factoring by grouping. I'm going to just go ahead and factor this in my head, but I'm going to attach a link on the calendar if you need a review of your factoring so that you can walk through the process of factoring by grouping. But here's what I know. I know that 2u times u is the only combination that's going to give me 2u squared. And then the only way I can multiply to get 1 is with positive 1 and negative 1. I need so that when I multiply this and this, I end up with a positive u after I add those together. So that means my minus goes here and my plus goes here. 2u times 1 would be positive 2u. Then negative 1 times u would be negative 1u. So when I add those together, I get positive u, which is what I wanted. So I'm not going to spend time here on the factoring. If that's what you need, then you're going to need to go back and brush up. I want to focus in on the process here. So once we get to there, we're going to use the zero product property. If this times this is equal to 0, that means one of two things. Either 2u minus 1 equals 0, or u plus 1 equals 0. And so that would mean that u is equal to positive 1/2, or u is equal to negative 1. Now, that's as far as we can go there. But here's where we have to go back to our original assumption where we substituted the u for the cosine of x. Now, if you can factor that without putting in the u's, go right ahead. To me, it helps to not have so many parts in there with all the COS and all, it's just a lot. So I like to put in the u's instead. Whoops. But again, do whatever you're comfortable with. So now what I need to do is put my u's back to what they were originally, which was the cosine of x. So I want to know, where does the cosine of x equal 1/2? And where does the cosine of x equal negative 1? The period for cosine is 2 pi, so we're looking at the entire circle. And so the cosine of x is equal to positive 1/2 at pi thirds. And then if I keep going, also at 2 pi thirds. Remember, cosine is positive in quadrants 1 and 2. So there's 2 of my solutions. It's going to be negative in quadrant 3 and 4, so I know I'm not going to get a solution there. Cosine is equal to negative 1 at pi. Remember, the ordered pair at pi is negative 1, 0. So pi is my other solution. That's the only place on the circle where I would get negative 1 for cosine. And those have to be my only 3 answers because we've looked at the whole circle and the domain that they wanted in general was 0 to 2 pi. If they wanted more solutions than that, we would have to keep trying. With the multiple angles, because you divide and make the angle smaller, that's why we have to start plugging in the ends to see what else. Like 12ths aren't labeled on our circle, so we had to go through and figure it out. But on this one, we're getting solutions that are directly off of our circle. So we don't have to do that end part because we can already visually see that we've gotten all the solutions off of our circle. Okay, let's look at another one. Go ahead and see if you can factor this one really quickly on your own. I'm going to set this up again using U substitution. So I'm going to replace my sine squared with u. So 2u squared minus 3u plus 1 equals 0 is what I'm trying to solve. This is going to be factorable. Again, the only thing that multiplies to 2u would be 2u and u. I can only have a 1 and a 1. But if I need to add up to -3, I need both of these to be negative. 2 times -1 is -2. -1 times 1 is -1. -2 plus -1, that's what's going to give me the -3. So there are my factors. So again, 2u minus 1 equals 0, or u minus 1 equals 0. Go ahead and solve for u. So u is positive 1/2, and u is 1. Now remember that this time we were substituting for the sine of x, so we're going to go ahead and plug in there. So I want to know, where does the sine of x equal 1/2, and where does the sine of x equal 1? Go ahead and look at your unit circles and see if you can come up with those values. So what we should be getting for x, sine is the y, so sine is positive 1/2 at pi sixths, and then also at, let's see, sorry, I lost my train of thought, pi sixths and 5 pi sixths. And then for the sine of x, we are looking at positive 1. That's going to be at pi halves. So there's our other one. That's the only place that we are going to be able to get solutions. So that is it. Now, I'm just thinking back really quickly. As soon as I said something out loud, it made me think about the previous problem. When we got to where, hold on. Yeah, I thought so. I misspoke. I apologize. I was looking at the sine value. Cosine is positive in quadrants 1 and quadrant 4. So those two solutions were originally incorrect. 1/2 gives you pi thirds and 5 pi thirds, not 2 pi thirds. I'm sorry. Go ahead and make that correction there. All right. I'm going to do one more example here. If you feel like you've got this, go ahead and move on if you want to try to work this one yourself and come back to it. But you can go ahead and look forward there. So this one you may or may not notice as a special product. This is a difference of two squares. If we take out the signs, maybe you can see it. This is 4u squared minus 1 equals 0. This would be 2u plus 1, and 2u minus 1 equals 0. So I'm going to have u equals negative 1/2 and u equals positive 1/2. So if those are sine of x, and over here the positive 1, the sine is positive 1/2 at pi sixths and 5 pi sixths, but then it's negative 1/2 at 7 pi sixths and 11 pi sixths. So we get 4 different solutions here for this one. If you go and something is not factorable, then you're going to have to solve it using the quadratic formula. That is not very commonly going to happen because remember, you're picking values off your unit circle. You're going to get things that are square root of 3 over 2's. you're going to get things that are 1/2 and square root of 2/2s. Those are really the only things you're going to end up with. So it makes them pretty predictable when you're doing the factoring. I hope you can kind of figure some of these out. It's going to take a little bit of practice, but I think that's where we'll stop for today.